Hello and welcome to this video on fitting a single factor with just two indicators. Can it work? My name is Geiser. I'm an instructor and statistical consultant with QuantFish, and on this channel I present weekly statistics tutorials. On Tuesdays I usually talk about an analysis in the Mplus software, and on Thursdays I address more general issues in multivariate statistical analysis, including factor analysis, structural equation modeling, multi-level analysis, and latent class or mixture modeling. If this is something that interests you, then please subscribe to this channel. Also, don't forget to hit the like button and to check out the description for additional free resources, including a link to my weekly statistics newsletter, as well as free courses that I offer through QuantFish. In this video, I want to talk about the case of having a factor model where you have just one factor that is measured by just two indicators or observed variables, like you can see here in this path diagram that I generated with the Mplus software. So let's take a look at this model in a little bit more detail, and let's see what issues may or may not come up with this model. There's a lot of confusion about models with just two indicators in the literature, and a lot of people are confused, and there are, so say, rumors that say you can't do such a model ever, you should never have just two indicators, that's always bad, it's always under-identified, you cause a lot of problems. And so that's why I want to address this issue here, so that you can see what the real deal is and what you need to be aware of versus what is actually not such a big issue in general. So let's take a look at the output file for this model. So I'm going to get out of the path diagram here. I'm going to show you part of the Mplus output so we can see what issue we ran into here. So you can see that when you look at about the middle of the Mplus output file for this two indicator single factor model, you can see that you get several warning messages here. You can see that Mplus reports that the degrees of freedom for this model are negative, which is not a good thing. For factor models and structural equation models, we need to have at least 0 degrees of freedom, 0 or positive. The model could be identified with 0 degrees of freedom. It would then be said to be just identified or saturated, and we'll see that in a little bit what that looks like. So that would be okay. Positive degrees of freedom can be okay when you have an identified model, but negative degrees of freedom can never be okay, because this means that you have fewer pieces of information than there are parameters to estimate, and then a model must be under-identified by definition. So the parameters of the model cannot all be identified in that case, and an under-identified model is something that you would not want to look at. Typically there are some things where you can work with those models, but in general you don't want an under-identified model, so you want to avoid that. So that shows you this model is not identified, and Mplus says that clearly here as well. So this is an under-identified model, and so as a result the chi-square test is not available, and there are other issues with this model too. So Mplus recommends that we check our model. Funny enough, you still get the message the model estimation terminated normally, which I guess in a sense it did, but not really, because an under-identified model isn't a model where you can get actual valid estimates for all of the parameters. You can also see that there's a warning message about the standard errors being untrustworthy, and that again that there are signs of model non-identification. So whenever you get a message like this in any software program, not just Mplus, then you should be very wary, of course, and you should check your model. Not every software program may even give you outputs. So there are other SEM software programs for which you wouldn't even get any output, and they would just simply say this model is not identified, you're not getting anything. So Mplus does give you some things, and you have to be really cautious because you shouldn't really interpret those things. So let's scroll down a little bit and look at some additional output here. You can see that the chi-square test of model fit has a negative degree of freedom and a value of 0, and so this again shows you that this is not good, but then you still get fit statistics as well, the RMSEA, the CFI, TLI, and the SRMR. And so if you're not cautious, you might scroll over this and say, oh, RMSEA is 0, that's great. Oh, CFI is 0.996, oh, fantastic. And SRMR is 0, so that indicates really good fit. So be careful. And you can see that Mplus even gives you parameter estimates, and you might think, oh, this looks okay, and even standardized parameter estimates are given. But then when you look at the standard errors, you can see that those are huge relative to the parameter estimates. So that clearly shows that there's an identification problem here. But some people don't look at standard errors, they only look at the estimates, and then you might get into trouble. So make sure you always check for warning messages. And now, in summary, we see that a single factor model with 2 indicators is not identified, at least not if you estimate one of the loadings freely. When we go to the model results one more time, you can see here that the second factor loading was supposed to be estimated, or Mplus attempted to provide an estimate for that loading, whereas the first loading was fixed to 1, it has no standard error, and it's exactly 1, but the second loading Mplus tried to estimate. And that is something that does not work when you have a single factor and just 2 indicators. It would work if you had a third indicator, then you could estimate 2 out of the 3 loadings freely, or you could leave all loadings free and fix the factor variance. That would be just identified. But with just 2 indicators, it's not. Why is it not identified? It's not identified because with 2 indicators, we have only 5 pieces of information that we can use to estimate parameters from. And you can see that in Mplus or other software when you look at the sample statistics, the descriptive statistics. You can see that with 2 variables we have 2 means which can be used to estimate the mean structure portion of the model, meaning here the intercepts of the measurement model. And we have the covariance matrix, which contains the variances of the observed indicators in the diagonal. So 68.57 and 59.63 are the 2 variance estimates for the observed variables, and then 40.17 is the covariance among the 2 indicators y1 and y2. And so we have in total 5 pieces of information, 2 means, 2 variances, and 1 covariance. But in a 2 indicator single factor model, we estimate a total of 6 parameters. You can see that here. This loading is a free parameter. And then we have 2 intercepts, which makes 3 parameters. We have the factor variance, which makes 4 parameters. And we have 2 residual or error variances estimated for the indicator. So in total, we have 6 free parameters here in our model. And that never works. When you have fewer pieces of information, meaning 5 pieces of information, but 6 parameters to be estimated, then you get negative. You get 1 negative degree of freedom, and then the model must be under-identified. So that's one reason why a lot of people say you should never use a factor model with just 2 indicators because it's under-identified by itself. However, that's only part of the truth. So that's not fully true, because you can identify such a model and you can identify it in more than one way. And so that's something that you should also know, because there are certain situations where we have only 2 indicators. There's just no other way. And then what should we do? Should we not use them? Should we combine them into an observed sum score and use that? That may not be ideal, because a factor model allows you to separate true score variance from measurement error variance. And so you want to still use that typically, that advantage of having a factor model. Even if you have just 2 indicators, you want to be able to separate true score variance from measurement error variance. And so there are ways to identify a single factor model with just 2 indicators, even in isolation. So even if you don't have other variables. And so I'll show you 2 ways to identify such a model. One involves adding another variable, but another way does not include that. So let me go to my Mplus input file and modify it accordingly. So when we go to the input file, you can see here's my factor model, factor measured by y1, y2 in my model statement. Mplus automatically constrained the first loading to 1 for identification, to set the metric of the factor. That's the default in Mplus and many other programs of structural equation modeling. Now, one way to identify this model without adding another variable is to assume what we call essential tau equivalence. In classical test theory, we have a measurement model of essential tau equivalence, which makes the assumption that two variables measure the same true score variable except for differences by a constant, meaning they can differ in their means, but they have the same units of measurement and they measure essentially the same factor, meaning they have the same loadings but not the same intercepts, so they can have different means. Furthermore, assuming that they are uncorrelated error variables like we typically assume in a confirmatory factor model. So this would be the assumption here, essential tau equivalence, meaning the variables, the true score variables for the two observed variables differ only by an additive constant. And so in that situation then, essential tau equivalence can be specified by fixing both loadings to 1. In Mplus, this works by putting the @1 statement here behind an indicator, and then both of these loadings will be fixed to 1 because the first one is by default already set to 1. Now if you want to make it more explicit, you could write @1 here as well, but you don't have to do that in Mplus because Mplus automatically constrains the first loading after the by statement to 1 for identification. So now the model is identified. Under essential tau equivalence, even if you have just two indicators, the model is identified, and we can verify this by running this model again with both loadings constrained or set equal. And then you can see when we scroll down that there's no longer a warning message about non-identification here before the fit information. And then you can see the chi-square test of model fit now has 0 degrees of freedom, no negative degrees of freedom. 0 means the model is saturated or just identified, and that's fine. We can use just identified models. They can be valid models. We use saturated models all the time. For example, multiple regression models are saturated. ANOVA, analysis of variance models, are saturated. So there's nothing wrong with that. We can use the parameter estimates because this model is identified. It's not testable here with just two indicators, which is a downside. So you cannot test whether the assumption of essential tau equivalence here really is reasonable. This would have to be a theoretical assumption saying, oh, for example, these indicators have similar metrics, they come from the same test, maybe they are parcels from the same test, or they are subscales from the same test, and the assumption of essential tau equivalence is therefore reasonable. So here the justification would have to come from theory rather than fit testing, because a saturated model by definition always fits perfectly. It cannot be tested against the observed data. So that's one downside, but other than that we can use the model, and you can see in the output now the two loadings are both fixed. The unstandardized loadings, the model is identified. We get the estimates of the intercepts, which in this case here just simply correspond to the observed means. We get a factor variance estimate, and we get the residual variance estimates. And so that might still be valuable information. For example, if you wanted to assess the reliability of the scales. So if y1 and y2, if you wanted to know how reliable are they in the sense of classical test theory, then you can use this model of essential tau equivalence to estimate those reliabilities, and in Mplus they are given as r squared. You can, when you scroll down to the completely standardized solution stdyx, you can see that we do get standardized factor loadings. They need not be equal, because in the standardized loadings we instead constrain the factor variance to be equal, and so we can estimate standardized factor loadings here. That's, so say, okay under the constraint of equal unstandardized loadings, and we get r squared values. You can see that the r squared values here are provided, those equal the squared standardized factor loadings in this model, and you can see that they give us an estimate of the reliability of each indicator, which under essential tau equivalence, the indicators need not have the same reliability. So this would mean that 58.6% of the variance in Y1 is true score variance, and 67.4% of the variance in Y2 is true score variance. So that could be useful information. So you can see a single factor model with just two indicators can be a very useful model if you can make that assumption of essential tau equivalence, if that's a reasonable assumption. Now, that may not be a reasonable assumption if you have two indicators that differ widely in their scales, for example, or if they don't measure the same true score variable, then of course that wouldn't be a reasonable assumption. But in many cases, it may be a reasonable assumption. Okay, now I promised you that I would show you another way that can also be used to identify this model without having to assume equal loadings. And so one other way to do this is by keeping the second loading free again, like we did at the beginning, but adding another variable that is correlated with the factor. And so here in this case, I can pick from my variable list another variable, let's say y3, and I can just simply correlate my factor with y3, and then the model will also be identified as long as y3 is substantially correlated with the factor. So meaning this correlation has to be substantially different from 0, so that identification will be provided indirectly by that correlation with y3. So let's take a look at that also. Now we have a model, so say with a covariate of the factor, and it's just simply an observed variable. It could also be a latent variable. So if you had two factors, and both factors had two indicators and they were correlated, then you also have an identified model. So let's take a look at this also. We can see again no warning about under-identification here, so that looks good. We can see the chi-square again has 0 degrees of freedom, so this model then also is just identified. We have now just enough information to identify all the parameters of this model, and that's fine. So say we can't test the model, but at least we're getting parameter estimates, and you can see that now the second loading can be estimated, even the unstandardized loading, because we now draw on information from y3 to identify the measurement model, and y3 is substantially correlated with the factor, as you can see here from the covariance. So in the unstandardized solution you get the covariance between the factor and the covariate y3, and it's significant. So this is a substantial covariance, and all the parameters are now properly identifiable. So that's another way. If you have a factor that has only two indicators and you cannot assume equal loadings, meaning you cannot assume essential tau equivalence, then you can add another variable to the model. As long as you know that variable is correlated with the factor, that variable will help to identify your model. Looking at the standardized solution, we can see that here we have a very substantial correlation between y3 and the factor. The correlation is 0.798, so almost 0.8. Very strong correlation, and that helps with the identification. Now, if y3 weren't correlated with the factor, then that wouldn't help you. So then the model would still be under-identified empirically if that correlation were too weak. So keep that in mind. You need a covariate that is substantially correlated with the factor. It doesn't have to be 0.8, but something like 0.3, 0.4, that would work. Maybe also lower could work. But so the lower the correlation goes, or the closer to 0, I should say, the more this model will be empirically under-identified. So in summary, is it true that a single factor model with two indicators is always under-identified? No, it's not true. You can identify this model either by constraining loadings to be equal, or you can identify this model by adding other variables to the model that are correlated with the factor. Those other variables could be simply observed variables, or they could be latent variables, other factors. That also identifies the model. So then that means that per se there is not an issue with having just two indicators. it can work. However, there are certain drawbacks. One is you have to face the problem that there could be either theoretical or empirical under-identification, as we saw. So you have to keep that in mind and place appropriate constraints or add other information to the model. And then also one other downside of models with just 2 indicators is that they are more prone to improper solutions, meaning they're more prone to resulting in improper parameter estimates such as negative residual variances. And so that is something that gets mitigated by having measurement models with more than 2 indicators, saying 3, 4, 5 indicators. They become more stable. And it's in general, it is a good thing to have more indicators rather than fewer indicators, as long as the indicators are good indicators, meaning unidimensional indicators of your factor. So in general, I would also say you should have more indicators if possible. However, if you cannot have more than 2, then you shouldn't give up your model. You can still estimate your model, and it's okay to do as long as everything works fine. There's nothing wrong with it, and as a reviewer, I would not say that you cannot do this. So keep that in mind when you have models with just 2 indicators. They're not per se bad, they're not per se under-identified. I hope you found this video useful to learn more about factor analysis and structural equation modeling. If you did, then please subscribe to this channel, hit the like button, and check out the description for additional resources and courses on structural equation modeling and factor analysis, and I'll see you next time.